In the previous videos, we employed L'Hopital's rule when we had indeterminate forms in which both the numerator and the denominator were going to 0. In this video, I'm going to introduce L'Hopital's rule for another indeterminate form in which the bottom and the top are both going to infinity. In fact, in other words, that they're both infinite numbers. And L'Hopital's rule for this indeterminate form is frankly identical. If the numerator and the denominator are both going to infinity, so if this is going to infinity and the bottom is going to infinity, then the limits again is just the limit of the ratio of the derivatives. So with that said, let's jump into an example. And let's look at the limit as x goes to 0 from the right-hand side of the square root of x times the natural log of x. Well, at first blush, we don't even have a ratio here, right? But we can always rewrite products as fractions by using negative exponents. So this is equal to the limit as x approaches 0 from the right of the natural log of x divided by x to the negative 1/2, right? So, right, because if a negative exponent here, it just means it comes up to the numerator. So these are truly the same algebraically. And now I've got if you will, a fraction, a ratio. And if I examine the behavior of the top, so the limit as x goes to 0 from the right of the natural log of x. Well, what is it equal to? Well, hopefully you have in your mind the graph of natural log. This needs to be solid in your understanding so you know the behavior of ln of x, since it comes up so often. And the natural log, its graph, looks something like this. And so as x approaches 0 from the right, so as my input approaches 0 from the right, my output approaches what? Negative infinity. And so this is equal to negative infinity. And the denominator, so if I'm looking at the limit as x approaches 0 from the right of x to the negative 1/2, well, this is the limit as x approaches 0 from the right of 1 over square root of x, and that also is equal to infinity. Actually, this guy's infinity, this guy's negative infinity. So, and this problem says, L'Hopital says, well, we've got to have the both going to positive infinity. But that's pretty easy to deal with because, one last little sleight of hand, this is negative limit as x goes to 0 of negative ln of x all over x to the negative 1/2. And now, since I stuck a negative in front of it, the top is going to positive infinity, and the bottom is going to positive infinity. We've met the requirements of L'Hopital's rule. And again, let me just show how I kind of that little sleight of hand, right? This negative would cancel out with that negative and truly be equal to this function here, right? This negative and that negative, if I brought the negative in, would cancel out, and I'd have exactly what's at the bottom. So by just a kind of a little slick move, I've got everything set up for L'Hopital's rule. And so this is equal to, well, I need to compute what the derivatives of these guys are. So the derivative with respect to x of negative ln of x is negative 1 over x, or if you will, negative x to the negative 1. Whereas the derivative with respect to x of the denominator is equal to negative 1/2 x to the negative 3/2. So according to L'Hopital's rule, this limit is equal to the limit as x approaches 0 from the right of the derivative of the top, which is negative x to the negative 1, divided by negative 1/2 x to the negative 3/2. And doing the appropriate algebra, canceling this out, this is equal to the limit as x approaches 0 from the right of 2 times x to the 1/2. And as x goes to 0, this is equal to 0. So we know that the limit as x approaches 0 from the right of root x times ln of x is 0. Another example, kind of doing this similar move, say the limit as x approaches infinity of x times sine of 1 over x. So we've got, in this case, if I look at these limits together, if I just tried to do this directly, I'd have the limit as x approaches infinity of x, well, that's an infinite number, positive. And the limit as x approaches infinity of sine of 1 over x, well, do a little bit of kind of reasoning here. We know that the input, as x gets really big, the input gets really small. This part goes to 0. And sine of 0 is 0. So this is equal to 0. So this is an indeterminate form, right? 0, this part is, this part here is going to 0, whereas the coefficient x is going to infinity. This is an infinite number times an infinitesimal number. That's an indeterminate form, but we can rewrite it, just like we did in the last example, as the limit as x goes to infinity of sine of 1 over x divided by x to the negative 1. And now the numerator is still, sine is still going to 0, but if x is going to infinity, its reciprocal is going to 0. And so this is actually the original 0 over 0 indeterminate form, and so we can use L'Hopital's rule. L'Hopital's rule says that we've got to take derivatives of numerator and denominator. So derivative with respect to x of sine of x to the minus 1. So this is, we've got a chain rule here. And so the derivative of the inside is negative x to the negative 2. And then the derivative of sine is cosine. So it'll be cosine of x to the minus 1. And the derivative of the denominator is negative x to the negative 2. So using L'Hopital's rule, this is equal to the limit as x goes to infinity of, on the top, we get a negative x to the negative 2 cosine of x to the negative 1 divided by negative x to the negative 2. And lucky for us, these guys cancel out. So this cancels with this. And so this is simply equal to the limit as x goes to infinity of cosine of 1 over x. And just like we did before, as x gets infinitely large, the input here is going to 0, which means, and so cosine, very close to 0, is close to 1, and so this limit is 1. So finally, what do we know? The limit as x goes to infinity of x times sine of 1 over x is 1. So just one final example to show how this kind of works with kind of standard rational functions with indeterminate form. We've got the limit as t goes to infinity of t plus 5 minus t 2t to the negative 1 minus t to the negative 3, all divided by, say, 3t plus 12 minus t to the negative 2. So I don't want to keep writing this over and over again, so I'm going to say let's let f equal t plus 5 minus 2t to the minus 1 minus t to the minus 3, and g is equal to the denominator, 3t plus 12 minus t to the negative 2. So the limit as t goes to infinity of f, well, that's an infinite number. That's finite, so their sum is infinite. And these two are infinitesimal. So this is infinity. Whereas the limit as t goes to infinity of g, well, same thing. 3 times t, if t is infinite, plus 12 is infinite, minus an infinitesimal, this whole thing is still infinite. So they're both going to infinity, and so L'Hopital's rule says I just have to look at the ratio of their derivatives. So f prime is 1 plus 2t to the negative 2 plus 3t to the minus 4. And g prime is equal to 3 plus 2t to the minus 3. So coming back over here, using L'Hopital's rule, this is the limit as t goes to infinity of the derivative. So 1 plus 2t to the negative 2 plus 3t to the minus 4 divided by 3 plus t to the 2t to the minus 3. And now what do we have here? Well, as t gets infinitely large, these guys are infinitely small, so they're approximately 0. And this guy is also approximately 0. And so in the limit, this is just equal to 1/3. So in the previous chapter, we would have had to factor out the values of t and work this out. So without algebra, but using calculus, we can use L'Hopital's rule and get that this limit is 1/3. So again, students typically pick up L'Hopital's rule quite quickly. Hopefully you did too. Best job is just to practice, do lots of examples, and you will excel at this technique. All right, best of luck to you, happy mathing, and see you next time.